All right, everybody, this is opening video for Unit 6 on thermodynamics. So we're going to run through some important vocab terms that I think we need to know for the unit. I think you guys know most of them, but we're gonna double check. Just give you the overview of kind of what we're talking about for the whole unit. Then we're going to go over sort of how we talk about energy in terms of chemical reactions. And then hopefully we'll give you a quick little introduction into something called calorimetry, which is an activity that we're going to do later this week in person. Okay, so first thing that this whole thing is based on is the concept of thermodynamics, which is basically the movement of heat, the transfer of heat from one thing to the other. This is all based on the law of conservation of energy. Right? And so what this says, basically, is that energy cannot be created or destroyed. It can only change form, or like be transferred from one thing to the other. Now, this is a law, right? So it happens all the time. It's always been shown to be true. But the issue is, right, is that this only holds true really, okay? So total energy of an isolated system is constant. All right, that's another way to say this. So the total energy of an isolated system. So isolated means like closed off to the outside world, right? So in reality, we're never running reactions in isolated systems. So energy is in fact lost from systems to surroundings in the real world. So while this law is true on paper, if we were to be able to collect everything, the reality of it is that we often lose energy in processes in open systems, which is kind of what the Earth is really, right? Okay. Other important terms that we need to know. Okay. Let's talk about energy in general, right? So in general, okay, we have two primary types of energy. We have kinetic energy, right, which is Ke, and that is usually the energy of motion. And then we have potential energy, which is Pe. And that is referred to as the energy of position, which is often referred to as stored energy. All right? So this is the classic physics example where you have the ball at the top of the hill, and right at the top of the hill it has, no kinetic energy but a lot of potential energy. Then you get it rolling down the hill, and it now is converting that potential energy into kinetic energy because it is moving. And then when it comes to a stop at the bottom, you've had that energy transfer, right? Okay. So how does that relate to chemical reactions? So in general, total energy of a system is kinetic plus potential, right? So energy is kinetic plus potential. But in chemical systems, it's a little bit different to think about kinetic versus potential, and a little bit better to think about it as, heat and work, right? Or chemical and thermal energy. So the two other examples that we want to look at are work, which the symbol is W, sorry. Heat is the next one, that's Q. So work is W, and work is force through distance. Right? So if you had to say, like, I don't know, move the couch in your living room from one side of the room to the other, right? And you had to kind of push it across the floor. That's work, right? You're going to apply a force to the couch over the distance of the room, however far of a distance you have to push it versus how hard it takes you to push it. You can calculate that out to be the work that you did required to do that. So that is a form of energy, okay? Another form of energy is heat, which we represent as Q. Now you might be saying, why don't we use H? Long story. There is a form of heat that we will call H, and we will get to that a little bit later, but for right now we got to use Q. It's a very specific kind of heat here. So And heat is basically the flow of energy caused by a temperature difference. Okay? So if you have two objects that are different temperatures, heat will flow always from hot to cold until those temperatures even out. Okay? This is why when you have a lot of people in one room, the room gets really hot. It's because the room temperature is usually, like 25 Celsius. Our body temperature is usually about 37 Celsius. We are constantly losing heat to our surroundings as humans, right, as animals. And so we will continue to do that until the room matches the temperature of us, right? Which is why we are constantly, as animals, generating heat, okay, to keep our bodies warm, right? Okay, so how does this relate to chemical reactions, right? So what I'm going to do is put in a couple pictures here. So we're going to insert a picture. And we're going to do this one. Okay, here we go. So overall energy is the capacity to do work, right? That's sort of the definition of energy in general, okay? And there are typically two kinds, as we just discussed, right? So here is potential, right? We have potential, we have kinetic, and together they make up the total energy. In chemical reactions, potential energy is thought of as thermal energy. In other words, it's associated with temperature. So the kinetic energy when we're talking about chemicals is, we kind of call it as thermal energy. The potential energy, and I drew that backwards, my fault. This is kinetic, this is potential, okay? So kinetic energy is thermal energy, heat. And that should make sense because when molecules are moving, right? When molecules are moving, that is what the energy is. And when they're moving, they're generating more heat, okay? Potential energy, though, is what we call chemical energy, and that is the energy stored within the actual chemical bonds. So stored energy in chemicals is within the bonds themselves. So if you want access to that energy, you have to break the bonds and access that energy, okay? Okay, so when we're talking about this total energy, right, this E, we actually call it internal energy. As I just said, E equals kinetic plus potential of a system. So it's really important that we understand the term system versus surroundings really quick before we kind of go on with this. The system is whatever you define it to be. Usually in terms of reactions, it is the reaction itself. And then the surroundings would be everything else, okay? That perspective can change depending on what we're talking about. And I think I've used this example before of, you're sitting around a campfire, right? So is that process gaining heat or losing heat? Well, your question should be, well, from whose perspective? Because from the perspective of you sitting in front of the campfire, then you would be gaining heat, right? You're warming up from the fire. But if the system is actually the fire itself, then the fire is actually losing heat to the environment in there. And in theory, it'd be the same quantity of energy that we're talking about. We're just simply talking about the direction of flow. And so it's really important that we identify what is our system, right? What is the thing we are talking about? Whose perspective are we working with, right? Now, energy, this internal energy, right? So E is what we call internal energy of the system, right? The total energy of the system, okay? This is what we call a state function, okay? There's a lot of state functions in thermodynamics. So what I mean by a state function is that the value of this energy, it only depends on the state of the system, not how the system got there. And it's way easier to describe with an image. So that's what I'm going to do here. Insert image, mountain. There we go. Okay. So looking at this image. Okay, this is a mountain, right? You're going for a little walk. Okay? As you are hiking up this mountain, okay, what we're saying is a state function only really cares about the bottom line, not how you got to that bottom line. So this is a great example here. You can think of the total energy of the system as the elevation, right? How high you are. So let's say you and I both decide we're going to climb this mountain, right? And, you know, you're feeling great. You're feeling like you're in good shape. So you pretty much climb straight up and make your way to the top, right? You take path B, okay? You know, my knees are bad. I'm kind of older, right? So I'm going to take path A, right? I'm going to go the easy route. I'm going to take my time, and I'm ultimately going to make it up there, okay? It doesn't matter how we got there. We both got to the top. We're both standing 10,000 feet high, right? So bottom line, we're both there, and we're both at the same elevation, okay? So whether we took the long road or the hard road or the short road or the easy road, doesn't really matter. It just matters that you got there. Okay, so even though my path was, you know, more than twice as long and probably took me twice as long to get up there, you know, bottom line overall, we made it to the top at the same point. Okay, and so what we mean by that is whether a chemical reaction takes 1 step or 50 steps, it doesn't matter because in theory, the laws of thermodynamics will say that the energy transfer is constant, right? That it holds true, that the conservation of energy holds true. Okay. So that's what we mean by a state function, all right? So basically what that means is if we want to talk about a change in energy, which we often do, we only really care about final minus initial, right? We don't care about the path at all. We just simply want to know where were we in the beginning, where were we at the end, what is that difference, okay? And so we can really just say total energy of this system is final minus initial. Now, in the perspective of chemical reactions, we would say final is really the products minus the reactants, right? So the change in energy of a chemical reaction is simply the energy that the products have minus the energy that the reactants have. So here's an example. We're going to take carbon plus oxygen. We're going to do a little combustion, and we're going to get CO2. Okay? And if we put this here, pictures, here we go. Okay? So my reactants, right, are here. Okay? And products are over there. So we get reactants to products. What happens is, okay, the reactants are up here, and they have actually more energy than the resulting products do. So when this thing reacts, the total internal energy goes down because the reactants had more energy, right? And so we're going to end up with a delta E of a negative number, a less than 0 number, okay? And that ends up giving us the thing. So this system lost heat, right? So just to kind of be clear, right, if we're talking about this, however much energy the system lost, right? So here the system lost heat to the surroundings, right? Well, how much heat? The value of heat lost from the system equals the value of heat gained by the surroundings, right? So what's different about it? The only thing different, okay, is the sign, right? The negative, positive sign, okay? That's the only difference. So from the perspective of the reaction itself, it lost heat, so it's going to have a negative value. From the perspective of the surroundings, right, it gained heat, okay? So you end up with that. So if we end up here, if we say that the delta E, that the E of the reactants is greater than the E of the products, then it's going to be exothermic. System loses heat. Okay? If we go the other way, oops, sorry. Right? Then it is endothermic, which means system gained heat. Okay? So what do we calculate to get the internal energy of a chemical reaction, right? So we can actually measure products and reactants energy and like do this math out and figure that out, but you may not always know that. So things that are pretty easy to measure, so this is the big equation, is Q plus W. So this is change in internal energy. This is heat. This is work. Okay? Signs in thermodynamics are arbitrary, meaning you put the sign on the substance, okay, or on the value. So the sign shows direction of flow, okay? So Q could be positive or negative. W can be positive or negative, which then means E can be positive or negative, okay? So what does it mean when each of the values is there? So if we have Q positive, that's when the system gains heat. Q negative, system loses heat. W positive, when work is done on the system. Work negative, when work is done by the system. Okay, so we're doing a quick example here to help us figure this out. This is actually the example from the textbook. So really quickly, let's put that in here. Okay, perfect. Here's our problem, and then we're going to go through it. We have a potato cannon, right? Which is basically a cannon device that shoots a potato. So it provides a good example of heat and work associated with a chemical reaction. In the potato cannon, a potato is stuffed into a long cylinder that is capped on one end and open on the other. Some kind of fuel is introduced under the potato at the capped end, usually through a small hole, and ignited. The potato shoots out of the cannon, sometimes flying hundreds of feet, and the cannon emits heat to the surroundings. If the burning of the fuel performs 855 joules of work on the potato and produces 1,422 joules of heat, what is the delta E for the burning of the fuel? Okay, so we want to talk about delta E equaling Q plus W. So we're told that W is 855 joules, right, the work, and we're told that Q is 1422 joules. Joules is a unit of energy. The big question is, what are the signs of both? Because if we screw up the signs, we're not going to get the right answer. So we got to be really careful here. So I think the easier one to look at first is the heat, okay? And if you look here, the cannon emits heat to the surroundings, right? The cannon being the system. So if the cannon's the system and it emits heat to the surroundings, it means it's losing heat to the surroundings. So I'm going to go ahead and put a negative sign here because I'm going to say that heat was lost from the system, from the cannon. Okay, now we got to think of work. Is the cannon doing work, or is work being done on the cannon, right? And I would argue that the cannon is doing work because it has to shoot the potato, right? If we were talking about the potato being the system, then yeah, I would say work was done on the potato. But in terms of the cannon did the work. So I'm going to say that this is also negative because the cannon did work. Okay? So if we put these together, delta E is negative 1422 plus negative 855. They're both in joules, so that should add up nicely. And that's going to give us a final answer of negative 2277 joules, which would make this overall an exothermic process. Okay? So it's all about signs. Okay? And positive versus negative. The next thing that we're going to work on later, and we're going to practice more of these, as we go, but the next thing that we're going to work on is a version of how we can calculate heat. So in this case, heat was given to you, right? They told us that it was 1422 joules of heat. They don't often tell us that. Sometimes we have to calculate that from a laboratory setting. And there's another way we can do that, and that process is called calorimetry. Okay? Calorimetry, right? And this is basically a device used to measure changes in heat of a system. And this word is derived from calorie, which is a unit of energy. We can also, just like joule. And then the end of that, metry is just measurement, right? So the measurement of we're literally measuring calories. This is a way to measure heat. So what we can do is if we burn stuff, basically, that's what we do here. We put stuff in a enclosed container and we burn it to completion. And we measure how much heat it put out, right? We can figure out heat changes, okay? And so that's kind of what we do here. So it's a way to kind of close off the system and measure this. So here's the formula for how we use calorimeters. So it's Q, heat, equals MC delta T. We'll talk about each one of these. So Q is heat, okay? M is mass. Delta T, I think, is self-explanatory, right? Change in temp, okay? C, okay, is going to be the specific heat capacity. Okay, the specific heat capacity. Okay, so what the heck does that mean, right? Well, so there's just heat capacity, but there's also specific heat capacity, and that's the one we really care about. So C is going to be the specific heat capacity, which is defined as the amount of heat needed to raise 1 gram of something 1 degree Celsius. You may have heard this definition before because it's actually really the definition of a calorie, right? The calorie is based on water, and it's the amount of energy needed to raise water 1 degree, okay? That's kind of where the unit calorie was derived from. So this is the amount of heat needed to raise 1 gram of something 1 degree Celsius, okay? Why do we care about this? Well, this is unique to each substance, right? It's unique to each substance. So basically, some things have really high capacities for heat and some things have really low capacities for heat. I'll give you an example. Water, it has a super high capacity for heat. And I know that because it takes a ton of energy to heat water up. And it also takes a really long time for it to cool off, right? So if I want to boil a pot of water, I got to boil it for minutes, right? It takes a while, okay? But it also stays hot, really, right? When you turn that pot off on the stove, how long before you want to stick your hand in it? Well, not very long at all, okay? Because it's going to be a long time before I want to put my hand in there because it's going to stay hot. With something like metals, they actually have a very, very, very low capacity for heat because even though they get hot really quickly, they also cool off really quickly. In other words, they don't hold heat very well, okay? So, you think about if you're like baking something and you have foil on top, pretty much you can grab that foil right off the top of it, 400 degrees right away because it's going to lose that heat right away, okay? This is why we have to learn about this and talk about this in terms of like industry and design and things like that. Think of a frying pan, for example. The bottom of the frying pan is usually metal, but the handle is usually like a silicone or some kind of a plastic. It's because we want the food to cook. So we want the pan to be metal In other words, we want it to get hot quickly, but we want it to transfer that heat and lose that heat quickly to the food so it'll cook. The handle, though, I don't want it to get hot, and I want it to resist changes in heat. And so that's why we make it silicone, okay? So if I want to figure out how much heat a system has lost or gained, if I know how much of it I have, if I know the mass of it, and then I can look up its heat capacity, right? That's a standard value that we can actually look up if you know what the identity of it is. And then I know how much it changed in temperature, then we can figure out the heat change. This is the activity we're going to do later this week, where you're going to have an unidentified metallic substance. You are going to take data, you're going to weigh it, right? You're going to take its temperature change, and then you're going to look up or solve for the C value. So you're going to end up measuring how much heat it puts out, okay? And you're going to try to identify that substance based on what we see, okay? Okay, I think that's a good place to stop for now. And yeah, so we're going to do this activity later in the week. Okay, look towards the end of, so this is chapter 7 in the textbook. If you want to look at practice problems, you can do a couple of the practice problems and try some of the calorimetry ones I think are on tap for the next class. Okay, and we'll see you guys tomorrow.